Good afternoon. From today, I would like to talk about LP properties of Stokes groups. So it is the LP-LQ decay properties a very important issue to show some global well-posed strength of nonlinear problem of the Navier-Stokes equations. But also this subject itself, it has some very interesting issues. So first, for simplicity, we consider the Rn case. So today I would like to talk about Rn case. Then, so problem is du minus divergence du ei is equal to 0, and the divergence u equals 0 is in Rn, and t positive, and with initial data x is in Rn. So we consider this evolution equation. Then, yeah, my approach, or the approach in this lecture, is always consider corresponding resolvent problem. Okay, here is maybe f is much better, therefore I write f. I done divergence b is equal to 0. Then if you solve this equation for lambda, some sector, lambda sector sigma epsilon lambda 0 is in a complex plane, and then some lambda naught, and here is, sorry, it's a radius lambda naught, then angle of this is pi, so sector sigma epsilon lambda naught is this one. Then, so if you have the solution B for any lambda ranging in here, then you can come back to U by Laplace inverse transform of V. Gamma E lambda. Okay, let's say B is also function of lambda and x. So lambda E lambda. Where gamma is a contour in C, exactly defined as by setting gamma is gamma plus and gamma minus, and gamma plus minus is equal to lambda, complex number, and then lambda is equal to some large number, lambda 1 plus r e plus minus I minus epsilon. And R range 0, infinity. The lambda 1 is a rather large number. In fact, the picture of gamma plus minus is the following. So this is lambda naught, and then there is epsilon. And then you take lambda 1 as enough, and then this way. So this is gamma minus, and this is gamma plus. So lambda 1, just you shift this contour to lambda 1 to right. Then gamma plus gamma minus is in. Here it is, gamma plus minus is in here. Okay. Anyway, later I'll prove this. But this is rather well-known things. For example, if you study the analytic semi-group theory, then the first you solve the resolvent problem, and then you by using the Laplace inverse transform on this form, you can solve the time-dependent problem, the initial data problem. This is a well-known procedure. But anyway, maybe I will prove directly. But this is one typical procedure to construct the initial boundary value solution to the boundary value problem through the resolvent problem. Okay. Talk about this one in the early part of my course. I forget. Anyway, first of all, Stokes equation. We have to treat this, because, and also pressure Q. Why? Because usually the evolution equation means that the time derivative. So we have dtu, but we don't have dtq. We don't have it. So we have to reduce these equations in some sense only v by using this condition. Meaning is that we have to eliminate q by using v, right? And then, okay, so formally, you can consider that the following way. If you take divergence f, then is equal to divergence of the b. And then now here is mu div plus nabla p. Sorry, mu is here. The well-known formula d dv is Laplace d plus nabla dv. If you calculate this down directly, then you get this formula. Therefore, under this constraint, you get the df equal to mu, df is equal to everything b for b because of the divergence free condition, so you have Laplace p. Then you solve this equation, and then you plug this formula into here. Okay. Sorry, now I write maybe better to q. Excuse me, q. And then you plug this formula into here. So in this case, it's the f is modified. Right? And then you get the equation only for the b. So this is the fundamental idea. But of course, q is okay. If you do this, then you need the regulative f. But at least we want to solve this equation in LQ. Q is between 1 and infinity. Therefore, we have to consider the Laplace equation in the weak sense. So this is first point. Anyway, so instead of this, we consider the u minus phi is equal to phi. And then here is this inner product. It's real inner product, I consider. This is inner product in Rm, L2 inner product. But I consider real. No, sorry. No. Usually also you can consider the compressed conjugate here. But I prefer without compressed conjugate. Anyway. Okay. And then this equation for A in phi, then what is here? I mean, this is so-called weak Dirichlet problem. Oh, sorry, weak Laplace equation with weak Laplace. And then this space, of course, should contain in X C0 infinity function. Why? If f C0 infinity, then integration by parts. Just so Laplace u phi is equal to phi. Just gradient. And nabla is going to here, the divergence. And also nabla phi is here, is the Laplace. And this for A in phi, therefore, in the distribution sense, you have this equation. So you satisfy this, the distribution sense. So okay, so you satisfy this equation. But we need more. I mean, because of we need uniqueness of a solution to this equation, then we need more data here. Okay. So usually, if you want to solve the equation, it's on two is a small class is much easier. But the uniqueness, you need large spaces. So just you have to find the suitable class which guarantees that unique existence, right? So then what is X? In this case, X in our case is so-called we want Q, dual space QRN. So sorry, I'm sorry, I cannot explain why I choose this one. It's very standard, traditional. But anyway, H hat 1 Q prime is phi Q prime local. And then gradient phi is in LQ. Usually, X is chosen this space. So we call it weak Laplace equation. Is nabla U, nabla U, nabla phi is equal to F nabla phi or N phi H hat 1 Q prime. This is a weak Laplace equation. Then you can show that the following theorem. Or any this unique U which is a solution such that you satisfy this weak Laplace equation. And estimate sometimes. So this is a starting point of the discussion of evolution equations of the Stokes equation. So here is one. How to prove? First of all, I don't want to prove back the one lemma. Infinity Rn is is between 1 and infinity, then Schiller infinity Rn is dense in this space, namely any phi sequence zero infinity Rn not jump Rn minus phi and q. This sense, so zero infinity Rn is dense in here. Maybe, excuse me, maybe this is rather well known, but for example, where now my book is published, but it is Japanese. Sorry. This is my name. So, just published its appendix, for example. But maybe to prove this, I get some hint from some papers, but I forgot. Okay, so Daniel, maybe please believe it for a while. Sorry, I'm sorry. I don't know whether the reference of this, maybe for example, Professor Garde's book, maybe. Giovanni Paolo Gardi. This book, almost all the important things, important facts are proved in this book. Very big books. Maybe you will be able to find some proof or suggestion how to prove. But anyway, this is known, quite well known result. Then, why I indicate this lemma is this is a form. So for lemma is true. Then divergence U is equal to 0 in Rm is distribution sense, and only if U over phi is equal to 0 in phi. So this means that for U equal H1Q case, divergence U equal 0 condition is just this weak formula you have. In fact, it's easy because in fact So I already said that Caesar infinity is, of course, the subset of this. So if you take phi, so first maybe this one, then to nabla phi. I already mentioned with phi or n path. So this means that the dv equals 0. Take Caesar infinity function phi, and of course, there is a side of this one, this space. And then from assumption, this is 0, you nabla phi. And then just the integration by parts, you have divergence, sorry, you have dvu phi. And then for any phi, meaning is that the distribution sense, this becomes 0. So this part. So also they use this lemma. For any phi. Sorry. You take the sequence. You take this sequence. Then you nabla phi is equal to limit k nabla phi n, because u belongs to h1q. Therefore, you have this. Nabla phi n is going to nabla phi, converges to nabla phi in the LQ prime node. So you have this. And then here is phi n is a Caesar infinity function. Therefore, in this level, you can make the integration by parts. Phi n, right? And then this is 0. So you get this. So once you proving this lemma, then this lemma is trivial. Okay. But it's important. This lemma is very important. So instead of divergence-free condition, usually we introduce a solenoidal space. So solenoidal space is the following: JQ Rn is equal to U LQ Rn, and then U nabla phi is equal to 0 for any phi. So this is a weak variant of divergence U equals 0. Okay. Weak formula of divergence. I'm sorry. So this space is called solenoidal. JQ is called a solenoidal space. Then so-called Helmholtz decomposition is the following. Helmholtz already proves the following decomposition theorem. Meaning is that for NF, let's say you find phi. Sorry, not psi. What? Number of psi. Phi is equal to f number of phi for any phi. Given any phi, you can find uniquely the psi in this space, which solve this weak Laplace equation. I'm sorry, I have not yet proved this one, but anyway, maybe. I have not yet proved the theorem, but anyway, first we use the theorem. You can find this psi. Then so-called P F is equal to this F minus psi. Sorry, grad psi. Is of course this number of phi is in LQ. Therefore, this is LQ because phi h hat 1, meaning is that the number of phi belongs to LQ. From the definition of h hat 1 q. So then, of course, from the definition, it follows immediately that p phi number of phi equal to 0 for any phi. The meaning is that P is a map from LQ Rn N to solenoidal space. And then if you write Q, is also LQRN H hat 1 Q just F this psi that one. Then F is decomposed P Q F plus nabla Q Q F. Just this is Q nabla Q F. So this decomposition. This is we call it Helmholtz decomposition. Then, if you come back to this equation, and now for simplicity we write. Okay. Excuse me. come to this equation, if you consider again this equation, then already you maybe you already understand that if you take P is this solenoidal gradient part, then you have this equation. So we can eliminate pressure. Of course, right-hand side have some restriction. And then you find U is in JQ intersect H2Q. Intersection of this. Then, of course, automatically, if you find this U, then this the automatically divergence U equals 0, right? U is belongs to JQ, and then also H2Q. So I already mentioned that. So especially divergence U equals 0 on this. And then, of course, therefore, what we have to do is the following. For any F in this solenoidal space, there exists unique U is in JQRM intersection QQRM such that you satisfy sorry, I forget information about lambda. And then epsilon pi over 2. Then for any f and lambda, excuse me, lambda, this is just this is one of the goals of today's lecture. you understand the story, right? So we deduce the Stokes resolvent problem for Stokes equation is this problem. So meaning is that without pressure P. But then, of course, data, you have to take the data from here. Then you can find the solution uniquely in this solenoidal space. But then, so whenever you consider the equation on solenoidal space, you don't need pressure. It's a whole space case, Rn. Okay. I want to mention a tool which I use to prove this. So already mentioned several times, I guess, Fourier multiplier theory. To prove this. So MC is a Shinketing function and satisfy the multiplier condition. Satisfy and let MC is a function, infinity function, Rn except for 0. Then MC satisfies these conditions, multiplier condition. For any alpha, multi-index alpha. It's constant. You take MC, then you consider Fourier multiplier inverse XC hat XC inverse transform. This is a Schwarz class. So this is definition. Then this is Fourier multiplier. This is called as Fourier multiplier. Then for any p just between 1 and infinity, any p, any p, there exists some constant essentially depending on this exponent p, such that this TMF, P norm of this TMF is constant times alpha 2n plus 1 G alpha P. This inequality holds. Here, of course, C alpha, this C alpha is so you can calculate essentially you can calculate the bound, which essentially depends on the P and this constant. So this is so-called Fourier multiplier theory, which is usually we call this theorem is Marcinkiewicz, Hermann, Michelin Hermann. You can find proof. For example, Hermann's book. He wrote four volumes. Maybe Hermann wrote several books, but one of the most famous books is he wrote some kind of study of PDE. It's volume 1. You can find proof of this. I cannot say any comment. Maybe this is YouTube, therefore if I say something wrong, then maybe people think about I don't know, think that I'm stupid, but anyway, as far as I know that Marcinkiewicz is a Polish mathematician before Second World War. He proved Fourier multiplier theory is series case, Fourier series case. And then Michelin, the Russian mathematician who proved this, maybe resolving or some, no, not resolving. Another extension exists, but essentially Michelin proved this. And then Hermann proved also the same theorem, much elegant way, more readable way in some sense. And then if we want to know the proof in Japanese, then also please my book, Web Integral. You can find the proof in this book, Japanese book, with Japanese, in Japanese. So Daniel see some book, the Hermann, maybe. Okay. Anyway, I want to use this. Then how to prove? Okay, now we are consider it's solenoid. And then a priori we are expected that U satisfies divergence U is equal to 0. We expect this. Therefore, under this condition here, mu du is equal to mu Laplace u plus nabla du. But under this condition, this vanishes. Therefore, essentially this one. So we want to solve this equation under this condition. Therefore, as an equation, it's enough to consider this one. Then, first you define the solution to this equation, And then under this condition, you prove dvu is equal to 0. Then everything is fine. So first, we can solve this equation. But then, this is usually whole space. Therefore, you use the Laplace, Fourier transform. So generally, this notation is a Fourier transform. So you apply Fourier transform to this equation. Then you have this algebraic equation. So U is you can define this way. You can define the U by this form. Then we need one lemma. You have this lemma. This lemma is used to estimate the dominator of the. Yes. Lambda, sorry, excuse me, maybe I don't define. I have not yet defined this or already defined long time ago. This set, complex number without 0, and then the argument of lambda is time line. It's just a sector. So the lambda is written I theta. Yeah. Okay, any lambda here. And then theta is just between theta, absolute value of theta and the time side. Yeah. So this is the representation of a complex number with polar coordinate. Yeah. Okay. Theta. Length is lambda. Then lambda plus a absolute value square lambda plus cos, lambda theta plus a plus I theta. Therefore, it's lambda cos theta plus a square Yes, lambda. So it just continue to calculation. It's 2 lambda a cos theta a square. Now, cosine theta is here is minus pi, pi. So it's like this, and then minus pi minus epsilon, pi minus epsilon. No? I'm wrong. So therefore, cosine theta is sine pi minus epsilon. Right? Maybe this picture is wrong. And this is cos pi cos epsilon minus sine pi. I'm wrong. Yes, sine pi sine epsilon. Maybe this picture is wrong. This is minus. Cosine theta is, excuse me, opposite. この図は間違ってるか。これは正しいです。コサインシータは、is, better. Sorry. This is correct. So cosine pi is bigger than if the theta range here, then cosine theta is therefore this is lambda square minus 2 lambda a cos epsilon square. So you write in this way. It is identity. Then cosine epsilon is a positive. So you can write this here. Right? So this is a positive number. So you have 1 minus cos epsilon. And then well-known formula is equal to much bigger. Yeah, so-called A square is this is the inequality, trivial inequalities. Therefore, you have. So you take square root. Start here. We start here. We start from here. This is estimated by this one. So you take square root. You have this. Then so I want to define U itself is a Fourier. Okay, so then come back to here. So I want to define U by using the Fourier inverse transform. Therefore, what do we have to check is multiplier condition. We have to check we can show 1/2 1/3. We can get this inequality by using this one. G alpha is some constant depends on alpha, and then you can get this one. C alpha is a constant. And data to how to prove it. So in order to prove this inequality, we use so-called Bell's formula. I think my experience, Fourier multiplier theory is very, very useful. Only the point is that to check this condition. But to check this condition, usually we use the Bell's formula, meaning is that ft is maybe C infinity function, and then you consider this composite function, differentiation of this composite function. You can write in this way. Alpha if else derivative of f gc times some plus alpha L equals alpha, and then alpha I is positive. Then there are some number coefficients depends on alpha times d alpha 1 g xc alpha L gxc. This is so-called Bell's formula, I think. I don't know. I call Bell, or I guess I heard this formula is called Bell's formula. But who is Bell? I don't know. I'm sorry. But how to prove? Just you consider, for example. So this means that the derivative alpha is L order derivatives come here. Then you have some product of derivative G, L product. And then after that, so first you differentiate L times, and then after that, U minus alpha minus L. And then this alpha minus derivatives come to this product. Okay, so for example, if you consider FCG, then this is F prime GC and DXCJ. And then secondly, DXCK, DXCJ. And then the CK come here. You have and then CK come here. Then you repeat this one. Okay. CL. And this derivative come to here. Then you have third derivative. And then everything. And then CJ come here. Then you have GC. And then DXCL. DXCJ. CK. And then finally, DXCL come to here. Maybe I don't know. Maybe that's it. And also maybe, sorry, I forget one thing. Here it is. So DXCL come to here. So yeah. Anyway, important point is that three derivatives always come to here, then you have three products. Right? And then one derivatives come to here or here, then you have this one. And then all the derivatives come to here, then you have this. So meaning that here is only one derivative, then all the derivatives from B. And then alpha minus one derivatives come to here. Then the one second derivative and the other is first derivative. So you can read it this way. All right. Then how to use? I'm sorry. Then how to prove this? FT maybe lambda plus mu t inverse. Then x alpha lambda plus mu sorry mu. Therefore, I'm sorry. Maybe it's better to write T inverse, right? Then anyway, T inverse is now lambda plus c squared. Sorry. Maybe T inverse is much better. Why? Because it's constant. Then C alpha 1 so then you don't care about this one. Yeah. Because the lambda is constant. And the mu is just outside. So then how to calculate this one? First, you just note that first derivative c squared is c. Right. Maybe this way. At least. At most. Sorry. At most. Zero over c. Right? And the second derivative. This is constant. At most. And the third up to the m is greater than 3. So here only it's enough to consider first derivative and the second derivative. Yeah. Then it's enough to consider the special case. So alpha to alpha k is 1 and alpha k plus 1 alpha l is 2. You consider this a special case. Then what happened? It's so then of course the plus alpha k plus 1 plus alpha l is alpha. So this means that this is k and plus this is 2 l minus k is equal to alpha. Restriction just maybe it's better to write in this way. That's same. So you can calculate k. Every k is 2l minus alpha. Therefore, this big C alpha 1 C square E alpha L C square is, for example, in this case, you write C k, right? And some constant and then maybe L minus k. Anyway, then k is this. So sorry, alpha. So here it is. And then if t is 1 over t, so if L t is minus 1, minus 2, minus L plus 1 to t to the minus L. Yeah. Importance is just order. Coefficients you don't care. Therefore, you have C alpha and plus mu C square to C alpha equal 1 plus alpha. Now, lambda plus mu C square minus L. And then times lambda 2L minus alpha, right? But 2L minus alpha is positive. This is positive number. Therefore, minus alpha lambda maybe it's not necessary. Oh. So, yeah. Equals. This is positive number. Therefore, you have this. Yeah. And lambda plus mu c square minus L is sine epsilon something. Maybe I'm wrong. Therefore, this then times yeah, different. Okay, we don't care about mu. Sorry. Sorry. Excuse me. So you have C alpha. Alpha. Especially I forget something. No, here it is minus 1, so maybe I'm wrong. Minus 1. T inverse L times is to the minus. Yeah. So I'm sorry that therefore here is this is L minus 1. Minus. So L minus 2. I have to especially lambda. This is correct form. I made. I'm sorry. Maybe I want to make a correction. I want to stop, but before stop, I make correction. It's a really important formula. This is correct. So thank you very much for your attention. I want to stop now.